Hello everyone, welcome back to Bytes of CSE. So this is our first lecture on process scheduling algorithm. This is going to be a series where in each lecture we will be dealing with one algorithm at a time. So today we'll be learning about the shortest job first algorithm. Now, as you can see in this screen, there are a number of processes A, B, C, and D, and they have their respective burst time given. Now, by this burst time, we mean that how much time each process will be spending in the processor. Now, as you know, that whenever a process needs to execute, that process is not readily dispatched to the processor. Instead, the process is made to wait in the ready queue, and the operating system, or the scheduler in this case, will choose one of the processes. It will schedule the processes to run one after the other, especially in uniprocessor system where there is only one processor. Okay, so depending on the various ways the scheduler schedules the processes, the scheduling algorithms differ. Now, in this case, we'll be learning about the shortest job first algorithm. And in shortest job first algorithm, what happens is the processes are, that is, the processes already in the waiting ready queue, are sorted according to their respective burst time, and the process with the lowest burst time gets to execute first. So in this case, the process with the lowest burst time is process number D, which has a burst time of 2 time units. Now, in order to find out how effectively the processes were scheduled, we need to plot a time chart. So that is which process started when and which process finished when, starting from a time point 0. So now we start executing the processes. So the number one process to execute in the processor is process number D, as I have told. So D is dispatched to a processor at time point 0, and at time point 2, that is 0 plus 2, that is this burst time, D finishes execution. Now at time point 2, the next process to be executed will be the process with the least burst time among A, B, and C. D is done. So among the three, B has a lowest burst time of 5 time units. So B will be dispatched at time point 2, and B will be finishing at time point 2 plus 5, that is equals to time point 7. Now at time point 7, B has finished execution. Now the next process to go will be the process with the shorter burst time between A and C, and since A has a shorter burst time of 10, A will be allocated to the processor at time point 7, and A will execute from time point 7 to time point 7 plus 10, that is equals to time point 17. And at time point 17, C will be the process to be executed, and C will execute from time point 17 to time point 17 plus 12, that is equals to time point 29. Now, based on this Gantt chart, we will need to find out some information. So what are they? Let's see. So here we have 4 processes A, B, C, D with their respective start time from this Gantt chart. So A started at time point 7, B started at time point 2, C started at time point 17, and D started at time point 0. So this is what we have got from the from the Gantt chart. Now we need to compute the wait time. Now what is the wait time? Wait time is the time difference, that is the time the process had to wait in the ready queue before it was dispatched to the processor. Or mathematically, we might say that wait time equals to start time minus arrival time. Now, in this algorithm, we have not mentioned what the arrival times are. So, by default, we'll be considering that all the 4 processes were submitted at the same time. That is, we consider that the arrival time of these processes were 0. So, now effectively, wait time becomes equals to the start time. So now the wait time of each process, that is A, it will be 7 for A, 2 for B, 17 for C, and 0 for D. Now, based on the individual wait time of each process, we need to compute the average wait time. Now, the average wait time is nothing but the summation of these 4 wait times divided by the number of processes. In this case, it is 7 plus 2 plus 17 plus 0, which is equals to 26, divided by 4. That is the number of processes, A, B, C, D, that is equals to 4. Next, we have another thing that is known as TA time or turnaround time. Turnaround time is the time the process took to complete its execution from the time it was first submitted into the ready queue. Or in other words, we might say that turnaround time equals to finish time minus arrival time. Now, from the Gantt chart, we'll again find out what the arrival times are, what the arrival time of each process is. So, in this case, A finished at time point 17, that is here. B finished at time point 7. C finished at time point 29, and D finished at time point 2. So, here we go. And just like average wait time, you need to compute the average turnaround time, which is again nothing but summation of these 4. 17 plus 7 plus 29 plus 2, that is equals to 55, divided by the number of processes, that is 4 in this case, which is equals to 13.75 time units. Now, what are the advantages of shortest job first scheduling? Now, shortest job first usually gives the better throughput than the other algorithms. That is, the number of processes to finish execution in a finite time frame is usually high in case of shortest job first algorithm. Now, let's take an example. Now, this finite time frame can be anything, but generally we say that in 1 second, how many jobs were completed. Now, let's take an example. There are 5 processes, P1, P2, P3, P4, and P5, and these are the respective burst times of each process. So, first, in case of shortest job first, what will happen? These processes will be sorted according to the burst time. So if we do that, sorry, the processes with shorter burst times are considered first, that is P3, P5. Now in this case, since P5, since P5 and P3 both have their respective burst time equals to 1. So if I had placed P5 before P3, it wouldn't have been a problem. In this case, since 3 comes before 5, so I have just placed 3 before 5. But if you want to do the other way around, you are absolutely fine with that. You can go ahead. Okay, now let's get to the point. Now see, in order, so all these processes will be completing one after the other. So the total time that will be needed to complete the processor 1 plus 1, that is equals to 2, 2 plus 3, that is equals to 5, 5 plus 5, that is equals to 10, 10 plus 12, that is equals to 22. Now if we take a cutoff time, say 10 time units, let's see how many processes were completed in this shortest job first by 10 time units. So, up to P4, all the processes completed by 10 time units. See again, 1 plus 1, that is equals to 2, 2 plus 2, that is equals to 5, and 5 plus 5, that is equals to 10. So P3, P5, P4 and P1, these 4 processes were completed at 10 time units, that is 4 processes were completed in 10 time units. Now let's consider, say we haven't done any sort of ordering, and this is how the ready queue looks like. Just like that, all the processes were submitted at the same time and the ready queue looks like this. By some means, by some random means, this was the order, the initial order. And now if we try to execute the processes at this order which is given, we have P1 which will be finishing at time point 3, and next P2 will be executing. So P2 will finish at time point 3 plus 12, that is equals to 15. So see, at time point 10 at 10 time units for this unordered sort of algorithm or whatever we say, the only process to have finished will be P1. That is, only one process had finished instead of 4 in case of shortest job first. So this is definitely better, right? And also shortest job first gives better average turnaround time and better average waiting time. Now this will be discussed when I discuss the other algorithms. Since this is the first lecture, you just get to know this one. We'll be discussing that again when we do the other algorithms. Now next, what might be the limitation of such a nice algorithm which gives a better turnaround time, a better throughput, and also a better average waiting time? The biggest problem is, see, let's take the example. This is just the example that we looked in the previous slide. That is, there are 5 processes. So accordingly, say this time P5, I make P5 to execute first, then P3 executes, then P1 executes, then P4 executes, and finally P2 executes. So they start executing now at just for your reference, now before P2 gets into the gets dispatched to the processor, P2 needs to wait for 10 time units. That is 3 plus 1 4 plus 5 9 plus 1 10. Okay, because these 4 processes needs to complete before P2 can be dispatched to the processor. Now at time point 3, a process P6 arrives with a burst time of 3. Now mind it, when P6 arrives, and again the scheduler will run the algorithm to sort the processes. Now P3 has a shorter burst time than both P4 and P2. So P6 will be scheduled before P4 and P2, because at time point 3 only P5 has finished execution, P3 has finished execution, and P1 is executing. So the processing of P2 gets delayed by 3 more time units. At time point 5, P7 arrives with a burst time lesser than that of P2, that is 7, which is less than 12. So P7 will be scheduled before P2. So the waiting time now becomes 3, that is plus 3 plus 7, that is 10 more time units. Next P8 comes in with a burst time again shorter than P2. So again P2 gets delayed, and in this way, at this time point, Pn has entered into the ready queue with a burst time again less than P2, and we consider that in between all the processes have a burst time shorter than 12. So that means all those processes will be scheduled before P2. So at this point also P2 is still waiting for its execution. So this is a very serious problem, that even if the average waiting time for shortest job first is pretty good, the throughput is still okay, still good, but sometimes with the processes with bigger burst time will need to wait for a long time if the other processes in the ready queue have a shorter burst time. So this condition is known as starvation, where processes with longer burst time needs to wait for a long time before being dispatched to the processor if the majority of the processes in the ready queue have a short burst time. So this is a limitation. Now, what might be the questions that you can face from this shortest job first in your competitive exams? Now, in competitive exams, you might not come across a lot of questions from shortest job first because it's a pretty straightforward algorithm, as you can see, but they might ask you questions on shortest job first, not directly but indirectly, like in this case. This appeared in GATE 2021 CAC paper, where three processes arrive at time point 0 with CPU bursts of 16, 20, and 10 milliseconds. If the scheduler has prior knowledge about the length of the CPU bursts, the minimum achievable average waiting time for those three processes in a non-preemptive scheduler, which is rounded to nearest integer, is so and so milliseconds. Now, in this case, they are not asking you, they haven't mentioned which algorithm to apply, but whenever you come across keywords like all the processes arrived at time 0, the scheduler has prior knowledge about the length of the CPU bursts, the minimum achievable average wait time, and non-preemptive scheduler. Now, what is meant by non-preemptive scheduler? Now, there are two types of scheduling. One is a preemptive scheduling and one is a non-preemptive scheduling. Now, in non-preemptive scheduling, generally what we have seen just now, that whenever a process is executing, the process will keep on executing until its completion. That is, a already running process is not stopped and another process is not dispatched at its place in case of a non-preemptive scheduler. So in case of preemptive scheduler, just the opposite happens. So as we have seen in the examples, that operating system was non-preemptive. The scheduler was non-preemptive. So in this case, let's find out what will be the average waiting minimum achievable average waiting time. That is, you always get to know that they are talking about shortest job first, because only in shortest job first the minimum achievable waiting time, average waiting time, is possible. So in this case, the process with 10 milliseconds will be scheduled first, next to the process with 16 milliseconds, and finally the process with 20 milliseconds of burst time. So this is going to be your Gantt chart. So the waiting time of P1 will be 0. For P2 it will be 10, and for P3 it will be 26. So all you need to do is you need to sum these up and divide it by 3. There are 3 processes, so this is equals to 36, and your answer is 36 divided by 3. And what is that? Let me know in the comments. So this is all about shortest job first, and there is a link given in your description box that takes you to a site that contains some questions about the scheduling algorithm. Now, you might not be able to solve all of them because I have that MCQ is about the other algorithms also, but you can have a look if you already know the other algorithms. So that's all for today. Thank you for watching, and if you like the video, please give me a thumbs up and share it with your friends. Goodbye.